Okay, so what I wanted to do was to go through the sequence of examples that are in the book talking about how to calculate the electric field between two parallel plates. Because we talked about in the regular class about parallel plate capacitors, and we had certain things that we've been given. We know that the capacitance is equal to epsilon 0 times the area divided by the distance. We also know that the electric field strength is equal to the voltage across the plates divided by the distance between the plates. So where the heck do those things come from? Well, it turns out you start with the problem that we've just talked about, which is what is the electric field at some point x distance from a field, a ring of charge. So that's the one we just did. It's 21.9, example 21.9 in the book. And what we saw was the electric field along this axis of the disk is equal to 1 over 4 pi epsilon 0 times q, which is the total charge on the ring, times x divided by x plus a squared to the 3/2 power I. So because of symmetry, there is no electric field in this direction. There's only an electric field. So this one's equal to 0, the total electric field. So there's only an x component of the electric field, and that's reflected in the fact that I just have an I vector. Now what we want to do is, we want to go from here, you kind of go in steps. You go from here, then instead of looking at a ring, you actually look at a disk. So what we're going to do is we're going to take a ring and we're going to just stack all those little rings of smaller radius and make a solid disk. And then from that disk, we can calculate what the electric field is along that axis of symmetry right from the middle of the disk. Again, it'll only have an x component because we have this radially symmetric disk, and therefore it all the components in this direction cancel each other out. Okay, now once you do that, then you can go to the case of a disk that has an infinite radius. So here you let the radius go to infinity. So then that gives you the electric field away from a single disk. Now if it goes out to infinity, it's like you have just an infinite plane. So it doesn't have to be round anymore. It can just be any surface that has no bounds on its dimensions. So we're doing it for a disk, but ultimately you can make it into any shape that goes out to infinity. And then what the final thing is you do is you take these two infinite plates, which we show as rectangles just because it's easier to draw, but they really don't matter what shape they are. So this is our parallel plate capacitor, which has ultimately in the limit would have an infinite dimensions, but in reality what we do is we have it where the gap between the two plates is much smaller than the dimensions of the plate. So it's not, the reality, in a real world we don't have infinite plates, but we can have two large plates that are very close to each other. So that's kind of the evolution of the whole thing. And when you read a book like this, you tend to just like, oh yeah, you go through it real quickly, but you don't look at it in detail. So that's what we're doing. We're going to do these problems that are in the book, and we're not going to leave out any steps. I force you to go here. Okay, So the first thing we're going to do is we're going to take a disk, and then, so the disk is actually this big, and we're going to take a little element here at some radius r, and ultimately we're going to integrate from r equals 0 to the radius of the actual disk. We're also going to assume that the disk is uniformly charged. Now, a lot of times you get the charge in a finite size disk. It may actually be on the outer surface, but we're going to assume it's uniformly charged in this calculation. So what we have is that the ring, instead of having a value of charge Q, like we did when we derived this one, 2119, we said there was a charge on the entire ring, and then we divided that into segments, ds segments. Here we're going to say there's a differential amount of charge that's on each of these rings that we're going to stack together. And that charge is going to be equally distributed around that ring. And again, we're going to do it on a, so what we have is the area of the ring. The area of the ring is going to be equal to, and we're going to use a differential area because we have a very small segment here. It's got a thickness dr. So the area is, you could take the inside, you could say it's equal to pi times, the radius, we'll say outside radius, which is the radius to the outer part of this ring squared minus the inner part of the radius, like that. And that would give you the area, the net area. Take the outer area, subtract the inner area. But it's approximately equal to, when this distance between the two inside and outside of the ring, it's approximately equal to 2 pi times the radius, and this is the average radius in the middle, times dr. So basically what you're doing is you're taking this ring and you're stretching it out into a straight piece, and the length of this is going to be the circumference of the ring, and the thickness is going to be dr. So it's 2 pi r times dr versus doing it the other way. Okay, so that's the area. Now the charge over that area, the total charge is the charge per unit area times this differential area. Or you could say the charge per unit area is the total charge divided by the area. This differential charge divided by the differential area, either way. So that gives you the dq. So dq is equal to this sigma. So what is sigma? Sigma is the charge per area. And if you think about a parallel plate capacitor, that's the way we normally look at it. We have certain charge on a plate, and we divide by the plate area to get charge per unit area. So that's not a new thing. Now then we go back to this equation here, and instead of using Q, we're going to use dq, and we're going, instead of having E, we're going to have dE, because that's the electric field due to this little element of area. So we're going to say that dE, and it's just going to be the x component because the y components cancel out, is going to be equal to, so we take the equation up above, which was 1 over 4 pi epsilon 0 times q, but we're going to use dq instead, times x divided by x squared plus a squared to the 3/2 power. Okay, and I'm not putting an I because I'm using this subscript notation. But dq is equal to sigma times dA, 2 pi r dr. So what we end up with is 2 pi r. I'm going to put the dr at the end, so it's 2 pi r times sigma times x from here, times dr. So that's the new numerator. And then in the denominator we have 4 pi epsilon 0 times x squared plus r squared to the 3/2 power. So at a given radius, for a given radius of this ring, differential ring, that's what the differential electric field is. Now what we're going to do is we're going to integrate that from the inside radius to the outside radius. So if we take the integral from the inside radius to the outside radius of this differential electric field, that's going to be equal to the integral from 0 to r of 2 pi r sigma x dr over 4 pi epsilon 0 x squared plus r squared to the 3/2 power. And then the things that are going to be constant are going to be, well, we can cancel those out because we've got 2 pi, and we got the pi's are going to cancel out, and the what they do in the book is they don't simplify this. They leave it as 1/4. So you're going to have, what you're going to have is you're going to have this term, which is the charge per unit area. You're going to have x, because that's not r. So we're integrating with respect to r, so we can bring the x out, and then you have 4 epsilon 0. The pi's cancel out, and what you do is you can leave the 2 pi inside, or the 2 inside, so you get 2r dr in the numerator. 2r dr divided by x squared plus r squared to the 3/2 power dr. Okay, so you can use U substitution. U is equal to x squared plus r squared du. Well, x is not varying, so we integrate that, or differentiate it as if it was a constant. So the only part we differentiate is this one, and we get 2r dr, which is what we have in the numerator. And I got too many dr's here. Okay, 2r dr, that's du. This is u. Now we could change the limits, which we should, because we're doing a definite integral. So when r equals 0, u is equal to x squared, because you put 0 in there, and when r equals capital R, you get u is equal to x squared plus r squared. So those are the limits. So we're going to have sigma charge per unit area times x over 4 epsilon 0. We integrate from we integrate from x squared, and actually this is going to be r, capital R. So we're going to integrate from x squared to x squared plus r squared of du over u to the 3/2 power. Okay, now, so we've got sigma x over 4 epsilon 0. Now this is u to the negative 3/2 power. So when you integrate it, you're going to get u to the negative 1/2 power divided by negative 1/2. Evaluate between x squared and x squared plus r squared. We'll cancel that out with that, so we're left with 2. So we'll have sigma x over 2 epsilon 0. This is 1 over the square root of u. And we evaluate that between x squared and x squared plus r squared. And finally, we plug in the limits. So we have sigma x over 2 epsilon 0, 1 over the square root of x squared plus r squared minus 1 over x squared. And the square root of x squared. And then you see this almost looks like what's in the book. What they do is they find a common denominator here. Well, actually, they what did they do now? Oh, this is 1 over x. So this becomes 1 over x. So if you multiply this by 1 over x times x, you get 1. There's also a negative sign here somehow or another. Oh, I forgot that I've got a negative sign up here. Where was it? Should have been negative sign. Oh, here, negative 1/2. So there's a negative sign out of there. It's a negative sign here. So when you apply that negative sign, they switch places. So you've got sigma over 2 epsilon 0. This is 1. X divided by x is 1. But you've got a negative times a negative, so that becomes positive. This becomes negative. And then you can, when you multiply this by x, you can then, let me just show you what they're doing. So again, they leave steps out. What they're doing is they have x over the square root of x squared plus r squared. Now if you multiply that by 1 over x in both the numerator and the denominator, like that, the numerator becomes 1. And the denominator, this goes inside as 1 over x squared. 1 over x outside the square root becomes 1 over x squared inside the square root. Like that. And finally, it's 1 over the square root of 1 plus r squared over x squared. So this is the final answer for that particular derivation. Okay, and that's equation 21.11 in the book. So what that's telling us is that for a disk of radius r, capital R, that the magnitude of the electric field along the center line is going to be equal to that number. Okay, so we've gotten to this point here. Now what we're going to do is we're going to make R, big R, go to infinity, because that'll make it so we're going to take the limit of this as R goes to infinity. And what does that do? Says if the disk is very large, then r is much greater than x. So 1 over the square root of r squared plus x squared is very much less than 1. Yeah, okay. So what happens is you get r squared goes to infinity. So you get the square root of infinity. I think I got an extra square root in there. So what happens is r goes to infinity. The square root of r squared over x squared plus 1 goes to infinity. So you get infinity squared over some quantity. So 1 over infinity, which is this one, goes to 0. And the equation for the electric field, the x component of the electric field, is just equal to sigma over 2 epsilon 0. So what does that mean? Well, what that means is that E sub x is not a function of x when R goes to infinity, or R is much, much greater than X. Either one of those. So here's our disk, and it's huge. It's a really big radius. What it's saying is that the electric field is actually constant. So again, if you made it into the plate and these dimensions got larger and larger and larger, what it says is the electric field is constant at any distance from the plate. This is a constant, which is kind of interesting because you wouldn't imagine that the electric field would stay, theoretically, it stays constant till infinity if the size goes to infinity. And what's happening is, as you go further out, you get additional bits of electric field added to them. You do go farther away, but you get more of the disk contributing. And so you have more disks to contribute, and they just balance out, and you get a constant electric field. Okay, so that's this part. So here it says, when you make the radius go to infinity, that the electric field is constant at any distance from the disk, which I'm going to call a plate. And the value of the electric field is equal to sigma over 2 epsilon 0. Okay, now we're going to go to here. We're going to look at two plates. We're going to assume that they have an infinite area. And they're going to be a distance d apart. Now, there's an electric field on either side of this disk. I'm showing it going to the right of if it's to the right of the disk, you have a force towards, or electric field towards the right. If you go to the other side, to the left side of the disk, you have your electric field going the other direction. So when you have these parallel plates really close to each other, now I'm going to expand this out just so you can see it better. So this is just a side view. These are the distance between the two plates, D. So this plate is going to have an electric field going this way on this side, and it's going to be constant no matter what distance I'm away. So it's going to be constant all the way from here to here, and it's also going to be constant going out this way. It goes out forever, and it also goes this way out forever, all the same size. Okay, then you have the second plate, which is charged oppositely. So because it's charged with the opposite charge, the electric field actually goes this way in towards the plate. So if it's negatively charged, the electric field goes this way. Now on this side of the plate, it goes in, but in the opposite direction. Maybe I should make this plate green. Okay, now further away, it's still constant. It's still going in towards the second plate. Okay, so let's review this here. We have the red plate. We have a constant electric field at any distance from the plate. The second plate, the green plate, doesn't affect the red plate at all. And the opposite is true. So we have these going upward from the plate, these going down from the plate, red. Now the green is the same way, except the arrows go the opposite direction because let's say this one's positively charged. Actually, I guess it would be negatively charged. And these would be positively charged. So, because they have to go outward from the positively charged plate. So here they're going inward. So on this side of the green plate, they're going in. Here they're going in to the plate. Here they're going into the plate. Again, it's constant because either these plates are infinitely large or the area of the plates is very large relative to the distance between the plates. And so what you can see is these cancel out. So here the electric field, let me get a different color. Here the electric field, the net electric field here is 0. So outside of the two plates, the electric field is 0. The same is true here. We have the green going up, the red going down. So the net electric field is 0. Now inside, because these plates are equally but oppositely charged, they're going to add together. So the net electric field between the plates is going to be equal to the charge per unit area divided by 2 epsilon 0 from the green ones, and sigma over 2 epsilon 0 for the red ones. And so between the plates, the electric field is equal to 2 sigma over 2 epsilon 0, or sigma over epsilon 0. So that is the electric field between parallel plates, infinite parallel plates, or approximately between finite plates, but where the distance between the plates is much smaller than any of the dimensions of the plates. So what we get is, if this is positively charged on this side, and this is negatively charged equally on the other side, then the electric field is going to go like that, and it's going to be uniform between the plates. So you can get right next to the plate, in the middle of the plates, next to the other plate, it's going to have exactly the same electric field, which is kind of a neat thing about parallel plates like that, to be able to achieve a uniform, unidirectional electric field. Now there's another thing you can do, is you can, there's two other, if we go back all the way back to the beginning here, there were some other things that we learned. Capacitance is epsilon 0 A over D, and electric field is voltage divided by distance. So the question is, can we derive those equations from what we have here? So let's think about it. If we have charge per unit area is just going to be the total charge divided by the total area of the plates. We know that capacitance is equal to epsilon 0 A over D. We also know that capacitance is equal to the charge per unit voltage. So let's set these two equal to each other. Q over D is equal to Q over V. Q over V from the definition of capacitance is equal to epsilon 0 A over D. But sigma is Q over A, or Q is equal to sigma times A. So if I plug that in here, I'll get sigma A for Q over V is equal to epsilon 0 A over D. And what else do we have? We have something else here. We have this one. The electric field. The electric field is equal to sigma over epsilon. So I think if I solve for epsilon 0 here, that'll be equal to sigma over E. So I've got sigma A over V. For epsilon 0, I put sigma over E times A over D. These cancel out. These cancel out. And if I solve for the electric field, that goes up here, that goes up there, you get electric field is voltage divided by distance. So we prove that one. And I think that might be it as far as this whole thing is concerned. So there's a lot packed into all these things. But let's kind of review where we went from. Example 21.9, which was the previous video, derived the electric field for a ring of charge. That's the charge on the ring. This is the distance from the ring, x. A is the, what is A? A was the radius of the ring, so that's really r. Then what we did is we stacked all these little rings together into a disk to find the electric field at some distance from a disk of finite radius. That's what the integration stuff we did here. We came up with this expression. Then we said, let's make the radius go to infinity so we have an infinite, a really large disk. So it's any distance from a really large disk or a small distance from a certain size disk. If you get really close to the disk, then instead of r going to infinity, r becomes much larger than x. So this term approaches a big number, and this approaches 0. So in those cases, you end up with the electric field is constant at any distance from that disk, if the disk size goes to infinity. Then we take those two disks and we place them close to each other. Now it actually doesn't matter whether they're close or not. I mean, the distance is irrelevant as far as the electric field between the disks. The thing about the distance here is that when the distance gets small relative to the area, the dimensions of the disk, then it approximates this behavior. So what happens is these electric fields on either side of these two disks reinforce each other between the plates but cancel out each other outside of the two plates. So we get a 0 electric field outside the plates and a constant electric field between the plates, which is equal to the sum of the two, and we get sigma over epsilon 0, and then we can use that as well as some of the other information to show that the electric field between two disks is constant, and it's just the voltage between the disks divided by the distance between the disks or the plates.